Okay, I think we should start now. So let me welcome everybody to our bi-monthly meeting and seminar of the Task Force on Digital Twin of Power System. My name is Ravindra Singh. I am a senior principal of distribution automation at National Rural Electric Cooperative Association and also the co-chair of this task force. So in today's agenda, we have a presentation by Luigi Vanfretti on the topic interactive model transformations for power system dynamic simulation. So Luigi is a full professor at Rensselaer Polytechnic Institute since July 2022. He leads research in electric power systems and aircraft electrification at ALSET Lab. Previously, he was an associate professor at KTH Royal Institute of Technology in Sweden and worked as a special advisor at Statnett SF, the Norwegian grid operator. He has held visiting positions at several prestigious institutions, including King Abdullah University of Science and Technology, École Centrale de Lyon, SuperGrid Institute, and Mitsubishi Electric Research Lab. His research focuses on power system modeling, simulations, stability and control, particularly in power grids and electrified transportation. He also works on synchrophasor technologies, software technologies, signal processing, system identification, and machine learning for power systems. Additionally, he provides consulting services through Vanfretti Consulting LLC. So before we start this seminar, I have one announcement to make. So we have our task force meeting scheduled for IEEE PES general meeting. So our seminar is scheduled for July 23rd between 11 a.m. to 12 p.m. In room 330. So if you are attending in person, I would appreciate if you attend this meeting. So with that, I invite Luigi to give the presentation. Thank you.
Thank you very much. And Hossein invited me to give this talk a few weeks ago. The funny thing is that you guys are meeting next week, and originally I had submitted this paper, this exact paper, for the general meeting, but the general meeting didn't think it was good enough to be present there. So I actually just presented this a couple of weeks ago in Croatia. And I like to say hi. I saw Jonas presented coming in. He's a great friend of mine, and also the Gian Belangera and Jan Masarejan, I saw them. So I'm sad that I won't be able to see you guys this year. It's too bad for me. Also, I don't have any funding. So anyway, if somebody wants to throw a bone over here, that will be very, very appreciated. Okay, so let me tell you a little bit about the story of this specific work. I've done these kind of things in the past, but this is a little bit different because really this was driven entirely by Glenn Haley. And Glenn Haley is he's a transmission planning engineer at City Utilities of Springfield in Missouri. And so I worked with him at a time where we were building a similar solution that focused on a proprietary tool, and he wanted to work with us on an interoperable solution instead of just proprietary. So I've divided the presentation in 4 parts, right? I'll try to give you an idea of why this is of use. Then I'm going to introduce you to the XSLT language. Well, not really. I won't introduce you to it, but I'll describe a little bit the technologies that we are using to be able to do this model transformation, right? And transformation is an important term because it means that you don't change the source models, you transform into a new representation, okay? So keep that in mind. And it's not a translation either. It's a transformation. It's something very specific from the, it's actually from the software engineering, model-driven software engineering technologies world, and the web technologies too. And the last part is how do you can trust these models? And basically, that is all possible because of the models where that are, the transformation is done to our Modelica models that have been validated. So I'll talk briefly about that, not too much, just two slides, and I'll give you some conclusions of the work. So as I told you before, one part of the motivation is really the current needs of my colleague, Glenn. Well, we're just friends that decided to work together with on this. So city utilities, you see that blue star over there, it's really in Missouri, so it's literally middle America, and it does both electrical power and gas and other utilities, internet and so on. And it serves roughly 265,000 people. Now, they operate within the footprint of Southwestern Power Pool. So this is the picture right here, and this is the footprint. And they're right here. Oh, no, this moved around. Sorry. That's not it. It's right here in Missouri, really in that edge. Sorry about that. Right. Right there in Missouri. So they, to do their planning and operational studies, they depend entirely on the models developed by SSP. And when you get the slides, you can click and find about the model development of SSP, how they do it. They use the PSS software. Now, when Glenn approached me, really is because he's a very experienced with PSS, but really he has found that the models in PSS and the tool is insufficient to guide decision making during important events. And one of the events that he gave me as an example is this Winter Storm Uri, where they will have greatly benefit of being able to integrate multi-domain models that integrate gas with the power grid, because they still had quite a bit of gas they could have dispatched, and they were not able to do that because they would need to do studies that it was just too slow to do it. So really, one of the things that Glenn is trying to do is to build integrated models of gas network and grid to be able to analyze this in dynamic conditions. So this is not sinkhole stuff that is steady state. We need to include dynamics of turbines and the supply. So we have to start somewhere. So some of the kind of scenarios that they normally do is analyze 18% drop in natural gas or 38% in coal using this SSP model, but they really need to do ad hoc scenarios as part of their planning. And really, they have to start with a model provided, and to develop these ad hoc scenarios requires good tools to be efficient, and this really is not available to them. Right? They have, some licenses of PSS, but just with what they have is not sufficient, and they're looking for a different solution. So to perform the analysis becomes really time consuming, and time is really a major factor for them because it's a small department and usually they need to provide answers within 2 weeks or less. So what he wants is really that the models to move across tools quickly with reduced human intervention. So you don't need an expert to make sure these things are actually working well. But also that they give you valid results from the behavior point of view. Like if you simulate a fault and you get the dynamics, these are valid. You're not getting garbage out, basically. And so while doing this model transformations, one of the quotes that he gives is confidence is the purity of action produced by a mind free of doubt. Really, it means that when you're moving the models, you need to know that you can trust them, so that you can have confidence on the analysis and not worry about modeling issues. Okay, so this is really from the point of view of Glenn, but since Hossein invited me and I am in New York, let me talk to you about what are the challenges of the status quo, and it's particularly for New York? So they have decided in New York a great idea of connecting all of these wind turbines. And they're going to be connected here at the bottom. So if you're not familiar with New York, I'm around here where the yellow starts. So if I drive, it's like 3.5 hours to New York City, and to go visit Jamba Serejani, it takes me like 4 hours. So I'm really in the middle. They call this upstate New York. I'm pretty far. Well, the connections, the flow in New York is really hydropower and nuclear power coming from the left and going down and down into the city, and hydropower coming from the north. So it's nuclear, hydro, and hydro coming from Hydro-Quebec. And they all go to fit New York City, and where you have Long Island here. Well, Long Island is basically a radial network, so you might see some problems then when you're trying to do these connections at the weakest part of the power network. In addition to this, there is a plan to add renewable resources. I forget if it's, I'm not sure if it's 10 gigawatts and 6 gigawatts of storage. This was put into law by the CL climate protection something. I don't remember the entire name. I think I have it later. Now, the new model, doing these kind of things really requires new model and simulation capabilities and tools. Why? Because you want to check what happens before you connect the stuff, usually, to avoid problems. And well, you would think that that is being done, but not to the point where you actually avoid problems. And so this requires models to be portable, a single model that can be used in different software tools to perform different types of analysis and ultimately support decision making. So the specific case of by friends in Agile is that they have a model in PSS E that they use throughout NIPA that is basically two files, a .raw file, a .dir file. But they also need to run real-time simulations with something called HyperSim, and those are .ecf files. And unfortunately, going from one side to the other is not a joke. It's especially for large models, to get the same results is a titanic effort. And Reza is there that could talk more about this if you have some questions. And also, David, I think. I forgot he's there. I just talked to him. Anyway, so what are the challenges today? We have vendor lock-in. We have few specific and proprietary tools that bound the models to that tool. So really, you're locked in. You can't really move things around to take advantage of things, having the same confidence that you'll get the same results. You don't have interoperability because the files retain parameter details. Okay, so you have in .raw and .dyr files, you have the parameters, but you really don't have any information about what is the behavior. And that means the equations that govern the dynamics of the system. And this leads to duplication and inconsistency. So you end up with, at least I think in NIPA Agile, they have like 5 different tools or more, and you need to you need to put a lot of effort if you want to get similar results, sometimes even re-implement from scratch. I mean, so this, at the speed that they want to do these new connections and this energy transition, this current status quo, this is not feasible to keep the speed that is required. So what is the consequences that we will have if we keep doing things the way that we do? Well, we won't be able to understand the dynamic performances of the new energy sources, and this will lead to unexpected consequences. I give you an example here. This is PMU measurements, and this is SCADA. The PMUs you would think is noise that you're looking at. That's not noise. That's a 13.8 hertz oscillation that comes up in a wind turbine. that comes up in wind turbines. This was in Oklahoma. They did a lot of work trying to detect this problem. This is due to converter interactions with the grid. And the only way to get rid of it, because they can't change the parameters of the controllers on the fly, is to curtail. So you have to curtail. If you have to curtail the wind, you have to ramp up the non-renewable resources. Great. You basically dig a hole. You fill a hole by digging a new one, basically. So this is one example. There's another example that I don't put in the slides, but is the example of PVs in Germany. If you recall, they had to retrofit the PV inverters because they had put over frequency protections and under frequency protections, and they didn't figure that out until it was too late. They had to retrofit 350,000 PVs, and it costed around 175 million euros to do it. I have the paper somewhere if you want to read it, but these things should be avoided by doing good engineering. And obviously it's not being done. Otherwise this wouldn't happen. And it's not being done well because the tools are really a great limiting factor. Even if the tools can do the analysis, moving the models is the major challenge. And this leads to increased cost because it's time consuming and expensive to develop and use models for new technology and of the systems. So there is a report that was commissioned by ICOM that shows this table of the cost of developing a new model in a single environment can go up to around $600,000 per model per tool. This is unsustainable. It's not feasible to keep up with the speed of development. And this is also suffers from a lack of interoperability because if you implemented it for one tool, it might not work with another one, etc. And even if there is a way of doing it through a new IEEE SuperGrid standard where you can somehow do it, well, the tools are not implementing, not all tools are implementing it. And furthermore, it limits it only to power system tools. Well, I need other tools to do analysis. For example, I want to do my analysis through Python. I want to do my analysis through MATLAB or whatever. So I need to move the models wherever I want. So the proposed solution is to use an unambiguous computer and human readable language to define models. For example, the wind turbines, and that is basically Modelica that gives us a separation between the models, mathematical description, and the numerical solver tool. Making the model specification free from implementations required by a software. What does this mean? Well, when you need to implement a model in a specific tool, you need to write the equations usually in so that they can be solved by a trapezoidal integrator. Well, that's really not the model. That's really discretization to fit a numerical solver. Okay, so there is an ambiguity of how each vendor does it in their tools. So the next goal is to combine with Power Grid model exchange standards, the ones that the only one that is more or less successful, so that we can leverage new tools for analysis. So that's the same CGMES. And the other solution is to try to automate this translation for actual engineering operations that we are very far from at this time. So Modelica, as I said, Modelica is not a tool. Modelica is a language. Think about C or C++ and how with C and C++ you have GNU C and you have Microsoft Visual Studio where you can compile C and you have Intel. So one language, multiple tools. The same thing with Modelica. The language is open access, so you don't have to pay for it like it happens with other standards. And you can access the language specification and is maintained by an association actively in an open way. You can actually see the discussions. You have a library of common components, blocks and whatever you like to. And currently there's 9 tools that support it. Among them, there are proprietary, Daimola, Model on Impact, Wolfram System Modeler, etc., and open source Open Modelica. And there's a vast number of open source libraries. One of them is the OpenIPSL. The logo is a little dog because it's free, as in free puppy. So if somebody gives you a free puppy, you have to take care of it. So this is my second dog, basically, because I have a real one. So this is a Modelica library for power system modeling that has a vast number of components to do phasor time domain modeling and simulation. We have, I don't know, like 15 exciters, not 2, things like that. And these have been validated against PSS E and some of them against the Federico Milano's PSAT software. And basically, you get all the benefits that you can do model exchange between the Modelica tools. And if you want to use other tools, you can use the FMI standard, which allows you to even run models in real time targets. You have a formal mathematical description, so you just get the equations. You don't have to specify an integration method. And you separate it from the solver. So basically, you can use multiple solvers. And using the IMOLA, simulations are as fast and even faster than PSSE. And you can look at this reference of where one of the new modern solvers for differential algebraic equations in the IMOLA were tested with a large grid model. Okay. So finally, what Glenn wanted to do? So his point of view is that, usually conventional power system, the models are going to be maintained on daily basis by SSP on PSSE, or some other people may use the Silent Power Factory. But these tools may lack certain features or the flexibility that the user wants to have, okay? It also happens that some users really don't have confidence using these tools for certain validation cases or use cases. So you can basically use PSSE and convert it to SIM, and then perform validations of the SIM model with these available tools to validate the SIM model. Then you can apply model transformation. After applying the model transformation, you have to validate the model, which is basically checking if the model works well, and you get a single Modelica file. This Modelica is basically a text file, so you can convert it with tools that allows you to transform XML to text. And based on that, you could use any of the Modelica tools to perform analysis. So you can do time domain simulation, you can do linearization, or you could even calculate the frequency domain performance. So you get all these features that are not normally that easy to, well, some tools, you don't even have them in them. So great. Okay, so here's how we do it. We will have SIM files that are XML files within CGMES. We have something called translation rules and XSLT. And we will use an XSLT engine, okay, called editx. And this will generate the Modelica file. So that's basically the overview. So XSL means Extensible Stylesheet Language. It's a styling language that for XML. And what XSLT stands from XSL transformation. So XSL transformation allows you to transform XML documents into other XML documents, other plain formats, plain text formats such as text, and that is what we're doing. So we don't have to build a piece of software that does the transformation. We use the existing tools that understand XPath, XSLT, and all of these web technologies, and we simply focus on building rules of the translation. So this is really the innovation in here, that we leverage all of these technologies from the web, basically, that were made for web development. Yes, the common information model is XML, is extensible markup language. It's normalized, it has common data using multiple types, linked using keys, and this is important in a second. And you have multiple files, so you have SV, state variables, DY for dynamic, EQ for equipment, topology, and state hypothesis. And basically, what this is just parameters, really. That's what it is, but that's how the sim is composed. So you can think of the CGMES XMLs as a relational database, and the same as a more limited XML. So it has less structures, it has node and subnode only, not many subnode branches, it has more rules, which are either parameters or keys, and is normalized, as I mentioned before. So you have all of these files, and here I'm giving you an example of the, I think this is the equipment file for the AC line segment. So this is the XML file, and you can see here the transmission line, and we have the shunt, we have the resistance, we have the reactance, okay? So what we decided to do is that for each component of the power system, so if we have a model for a transmission line, we will create one XSLT rule that will go and look for all of the transmission lines and map them to a component of the model of OpenIPSL of a line. And we do that with every single component. So the translation files is one for each of the OpenIPSL components. And what does it include? It includes buses, lines, transformers, loads, etc. So here you can see, if I open this in editX, you have the main, which is the one that executes the whole transformation. And here you have the rule for the lines. And when you look, yes. For the generators, okay, you have it's broken down into the different types of generators in the SIM standard. And then within this one, you have the one that you attach the control systems to it. If you look at the include file here, you will see that within the transformation file here, we're included all the transformation rules that we need to take into account. So XSLT is a declarative language. It will produce text files of these links components. So the result for the transmission line is going to be of this form. And this is basically an instantiation of the Modelica component, whose name is going to be L1. This is the name of the instance for this model. And you're going to parameterize it. So this is really the goal. The transformation rule, when we run it for the lines, is going to go from this stuff to an instantiation of the model within a Modelica file. And then you do that for all of the components. Okay, so how do we do this translation? You have the namespace that is a 3-letter code here, XSL. And this template will match a particular XML3 node, and the match is going to be all the components in your model or your system model that is called SIM AC line segment. Then you will assign variables to a function using using either what's it called? Sorry, you will assign variables, right? So you need the base impedance. You have to create this variable, and this is done through a function that defines the base impedance, okay? The output that we generate will have a node. It will have custom functions and built-in functions. So for example, to create names that are compliant with Modelica, we have a function called compliant name, and this basically uses the built-in function of concatenation, and it will call it It will use L at the beginning, and it will add the concatenated name corresponding to this as the specific line. And then to convert to per unit, we have, to format. This is for formatting and to convert for the per unit. So we will format the number, that's the built-in function. And then here we will take the number of the resistance, and we will divide it by the impedance, and we will format it as such. So this is the formatting of the number. And we also put flow control in this transformation. So if you do not have a shunt impedance, you assign a value of 0. But if you don't have shunt admittance, but if you do have shunt admittance, you have to split them on both sides. That's how we do it in the OpenIPSL model. We take the total shunt and we split it on the two sides. So that's how the rule is built. Okay, so up to now, I explained you for the transmission lines how we go through each of the components. I did it just for the transmission line. We go through each transmission line and we apply the transformation, and we generate this line of code for each of them in the Modelica file. Now, the next thing is to connect everything together, okay? And to connect everything together, we have to create another rule called connections XSL. And this will use the keys in the SIM files to connect the components. So each SIM terminal, so here you have a line, and each line has a terminal. So each SIM terminal has a subnode called SIM in SIM terminal equipment, conducting equipment, and it has a RFD resource attribute. So we can create these Modelica connect statements that look like this, where you're going to connect bus 12 to line 11. We can create those statements by applying the XSLT rule. So within the rule, we will match the key of the terminal through the command, find this bus index and match it to the bus bar section using the RFID. And this links the RFD resource to the XSL key and extracts the parameters, which in this case is the name, for example, line 11. So how this is linked then is that connections XSL will look for each terminal. Right now we look just for this case, okay? And it looks for the RFD resource. This is the foreign key of, in this case, is the machine connected to that terminal. So this is the primary key over here. And you go through the entire, all of the terminals to build the entire connection file, okay? So the main file we mentioned before is basically what executes the what is going to be used to perform the translation. At the main node, you will see the encoding that is used, and then we have parameters that, if you use this interactive tool that we're using, is basically the names of the files over here. So this points to the source SIM files. You just need to point it to the EQ file, and it looks to the DY, TP, and SV automatically. And it asks you to give a name to the output model, which is this one. Unlike all the other XSLs, this one actually has root access and can see all of the files. And the functions can access an all from the DY file and set aside parse and so on. So the other parameters that we have are required. So we're converting the model, but in the model, there is no simulation scenario. So if you run it, it should be flat. So we need to add a fault, for example, to create a simulation scenario. So to do that, we give additional parameters of the relative path to where all the SIM files are. And we have the frequency, the bus where you apply the fault parameters, and the duration of the fault and the base impedance. So that's it on the methodology. Basically, to illustrate how this works, you would need to have this edit text tool. The examples and code are in this website. And there is a tutorial step-by-step that is in this link. You need to have the OpenIPSL library, which is required because the transformation only says, hey, use this instance from OpenIPSL, but it doesn't have OpenIPSL. And you need a Modelica-compliant software. For this work, I use Daimola and Glenn uses mostly Wolfram System Modeler. So those are the two tools that we verified that it works with. So what do you do as a user? You basically move the XML files to the project directory. You click to transform a document with XSLT, so apply the rule, fill up these two parameter windows. This will generate a text file. You load the text file and OpenIPSL in the Modelica tool, and then you click on check to see if the model is syntactically valid, and also it has the same number of equations and so knows which is a requirement in Modelica. Okay, so I wanted to show you this. So maybe I should just close this to start. So that's edit X. Okay, that's here. And I'm just going to go and open project. It's already open. Well, it's already open, but you know, if I just do it again, it's open here. I go to the source folder where I have them, and I open this Sim2 Modelica main file, and it's right there. Okay, so here is the main transformation file, and as I showed you before, these are all you can see over here all of the rules that we apply. Okay, lines is here, and this is the information that I was showing you before on the flow control, for example. Okay, so it's pretty nice because you just focus on doing that. So if we go and we execute the transformation, this is already set up. So I'm pointing to sure. I'm pointing to the EQ file. So along with the repository, we have provided a number of examples to test. These are all SIM files generating from PSSE and then pass through ODMS. So ODMS generates this one. So we point to the EQ file and we tell it how to call this. So I'm going to call IEEE 14 demo.mo. Okay. I click on open, and then I go to the parameters for default. I'm going to leave this as it is. I click OK, and the result is already shown here. This is our Modelica model. So it's telling us that inside of this package, we're going to have a model called model IEEE 14. And inside of it, we're going to have all of these buses. And you have the base voltage of the buses. You have the starting voltage and angle for each of them that are coming from the SIM SV file, I think. Yes, the SV file. Then you have the conversion of all the lines, the conversion for all the transformers, shunt compensators, loads, synchronous machines. Okay, now the synchronous machines include controls. I will show you that in a second in Modelica. It's easier. And default, and then here you have all the connection equations that were generated automatically. And finally, we connect the fault, and that's it. And you see all of this other stuff is the power plant units that are created. Let me unload the previous one that I had done. So unload this. Now I have loaded here in Daimola, I have loaded the OpenIPSL, and I'm gonna load the resulting file that is on the repository sorry, not source, output, and it was called demo, right? So let's open that one. And when you see, this is now in Daimola, and you see now so some syntax highlighting that shows you the same conversion that we talked about. If you go to the graphics layer, there is no graphics for this example because we haven't created something that maps. There's another IEC standard that tells you how the one-line diagram should look, and that would need to be translated into annotations in Modelica. Okay, but in the textual view, you have everything. Now the generators is easy. No, sorry, it's not. It's easier to create a graphical description automatically for them because it's basically the connections of all of the how each of the generators are modeled with the turbines, excitation systems, turbine governor excitation systems, and so on. So you can see here we actually have a description of how each of these generators is modeled with their different components, let's say. Okay, so those are being called in the model here. So you're given the parameters of initial guess from the power flow, basically, from the state variables from SIP. So that's over here. So finally, I just have to click on check, and that does it. And it has done that. Of course, you can try to simulate. So if you click on simulate, in this case, so just is done. Yeah, it's done now. Just to simulate 10 seconds, generate the code, all that story that does here. So it actually let me perhaps do something else. You see there is a translation that is done here that goes from Modelica and generates C code and compiles a C code that then is executed. But it tells you what the translated model looks like, how many continuous time variables he has, how many algebraic variables he has, and the total number of equations and so on. And finally, you know, in Daimola, it's easy to plot. So this is a case where the condition that we have already makes the system unstable. It's intentionally, we made it like this because it's boring to look at flat lines. So this is much more nicer. So there's a video here to share with you if you want to take a look afterwards. The last part was validation, and this is just to talk about, we said before that when you do this transformation, you have to trust that your model is valid. So our OpenIPSL library has been validated against 5 different tools. It works mostly on those 5 tools. Here we're showing 1, 2, 3, 4. The validation results against PSS for this this WEG Gov. So it's a governor that we implemented for the WECC that is going to be implemented in or integrated into the OpenIPSL library shortly. So the ability to have this model in Modelica tools allows us not only to do time domain simulation, but we can do translation. And because, unfortunately, in the US, PSS is the de facto standard, we are now actually trying to, instead of doing SIM to Modelica, we're doing PSS to Modelica. Okay, so here's my conclusions. So what about SIM, CGMES, and Modelica? The CGMES version 2.5 Annex F, normatively, so I don't fully understand what that means, but what I understand is like if you want to, that's what it means. Uses Modelica together with the dynamics profile, so you can actually do this thing that we're saying, that in the SIM model you could say, for this dynamic component, use this Modelica library with these parameters. You can actually do that, but most of the SIM models haven't adopted. So the proposed method allows you to add Modelica models to existing SIM models during the transformation when Annex F doesn't provide them, or when Annex F has not been adopted. In North America, because SIM is limited and a lot of utilities lack the export tool. If you use PSS, you have to buy ODMS, and most people don't have that. So to avoid having to have that, we will have to do direct translation from PSS. You can look at this ongoing work that it's an old project that we're still trying to continue. If somebody wants to give me some funding to put some students to work on it, please do so. But really the goal of this is to be able to do PSS to Modelica transformation. We did it with NIPA Agile some years ago. Now, for city utilities, really what they want to do is to continue developing some tools to do this translation. This particular tool that I presented is for prototyping the transformation rules. So it's not necessarily something that you will use in production. This is more like something that you will use to check that whatever rule you're creating for translation is correct. And then when you implement it in your main tool for production, you can verify what you're doing. So that's the interactive sort of aspect of this, is using some a prototyping tool, basically. So this prototype tool gives you a very good insight of how sim files work and how to generate the Modelica models. And EditX offers a good environment to make this XSLT translations very interactive, clear, very expandable, and to gain insight of how the transformation is being applied. EditX is not free of charge, but you can even pay for the source, and a license is $20. So it's really it's accessible, you know. Interoperable standards, we think this Modelica and Modelica with OpenIPSL allows us to use these validated models in other tools, especially for tasks that are not available, which one of the main ones is linearization and frequency, where you usually have to do a frequency sweep. No, here we don't need to do frequency sweep. We do symbolic linearization, and then we can compute the transfer functions and calculate the frequency spectrum, basically. I showed you a plot previously. And so we are trying to, with these learnings, we're trying to enhance our PSS to Modelica prototype, eventually to support SIM, but that has become a little bit of a less of a priority for me because I'm in the US and I'm trying to convince people that use PSSE. What else can I do, right? Those tools are like a complement for PSSE. I don't think PSSE can ever be replaced, but you can use it for other things. So, for example, doing this multi-domain engineering or bringing your PSSE models into Modelica so you can run real-time simulations, which I can give you a reference of how it's possible to do it by having the Modelica model and put it in the FMI standard. Okay, what I told you about today, as I said, it was a conference last week, 2 weeks ago in Croatia. So if you have anything where you talk about SIM or Modelica, please cite our paper and the author copy, so you don't have to go through IEEE's paywall. You can find it in ResearchGate. So please cite it; it will be helpful. And voila, that's it.
Okay, yeah. Thank you, Luigi, for a great presentation. So if anybody has a question, there is a raise hand tab on the top. You can ask your questions.
Yes.
Yes, so I can get started. So first, thanks, Luigi. It was very insightful and quite clear as a presentation, so thanks a lot. I have 2 questions. The first one is about OpenIPSL. I see the last changes was in February in the repo. I was wondering what's the update frequency or maintenance of this library? That's the first question.
Well, where do you work?
Palermo.
Well, tell Jan Belanger to give me money to maintain it more frequently, instead of just giving money to Jan. Joke aside, if you go to issues, to pull requests, here we have some new models that are going to be integrated. So we have a model that we have actually validated in Power Hardware in the loop of the WECC RES models. So that's right here. We have a university campus real-world microgrids that we modeled with that too. So there's a bunch of things here that are waiting to be integrated. Right now, I have no funding to do this. So basically, I am doing some of the work. Fernando, that graduate, is doing some of the work, and there's a guy in Norway that helps us maintain it. So it's going to be slow. I'm hoping that we do a release this year. We do have a number of components that are in a different branch. Well, I can, I'm not sure how to show you right now because it's in Giuseppe's branch. Let me see. Giuseppe has let's see Giuseppe. So he graduated too, and in his repository, he actually has a bunch of components that have not been integrated. You see, OCT compliance. So he has a lot of new, where is it? Non-electrical, no. Electrical. So for example, if you hear controls, PSSE, you will see a bunch much more of the components that we have. So I'm hoping that it will happen this year, but of course everybody's doing it on free time. Yeah, so PSS we have more, you see.
Yeah. Okay. Thank
we
you very
have more. I'm not sure if I'm still sharing. Oh no, I was not sharing. I was showing the screen. You are showing the screen to show you where to find it.
Yeah, I saw it on my side as well. I understand. My second question is, at the early beginning of the presentation, you said that conversion from PCC to HyperSim was a titanic work. I was curious about what was the context behind this statement, because in the company we have added a feature to HyperSim, which automates this conversion from PCC to HyperSim, which was benchmarked and which also works with larger models. So I was wondering if you had met models where this was not sufficient, or if you had any feedback as to why it would have been
well, the problem is that usually you don't have full coverage, right? And you have done the benchmarking, but you know, you have to trust that it's true. So yeah, sure. If you can do all of it, good. But it's still, you're just transforming the parameters and into your own representation of HyperSim. You're not really using an explicit set of equations that have been defined in a language. You're just saying, here is my parameters from PSSE, put these parameters on a generator or whatever of HyperSim that is more or less the same. How much is the same? We don't know. And you're not really using exactly the same equations, right? So if you want to be strict, you can look at it that way. If you want to be loose and practical, yeah, fine, right? So it depends on how you look at things. Like, so for example, in the FMI community right now, the new FMI standard, they're thinking about exchanging reference results. So what this would mean is that when you generate an FMU from OpenIPSL, you should also include a simulation with a reference result from PSSE that was the source. And then you will compare if your FMU in HyperSim or your HyperSim model actually complies with the reference. Only that way you can actually check as an individual, as a user. Otherwise, it's based on trust, right?
Well, trust, and you have the models, you can rerun the benchmark if you don't trust the example, but yes, I get the idea. Just for information, we have it's not a direct copy paste from the parameter. We have a Python logic which can manipulate and adapt it to the destination, but in the end, indeed, PSSE has its own solver and representation. HyperSim has its own, and it's not necessarily the same .modelica file.
It's not. Well, it's not the same model. At the end, it's not the same model. If it's like that. So you can't really say that it's validated one-to-one. What happens with the Modelica side is that if you look at this, let me show you in here. If you look at the tests over here, so let's just go to something simple. Oh, let's do the renewable ones. The models are already there, you see? I forgot. So if you look at this one for the battery, this has already been validated against PSSE. We don't have it in the validation results online. If you want to find validation results online from us, you can go here and click on this one. That was the project that I'm trying to continue. So you can find here the validation results where we're comparing one-to-one to PSSE. How we are able to get the same result as PSSE in Modelica is because we have implemented components over here that you see, non-electrical functions, nonlinear, and so on, continuous. So these integrators, for example, these lead lags have exactly the same behavior as PSSE. And then when we compare, we use a second order method that is equivalent to a trapezoidal method. So that's how we can guarantee you we give you the same answer.
But did you have the same equation as PSSE? Do you get access to the internals of the...
No, we reverse engineer it.
Well, in this case, it's similar to the job that we are doing, because you create the model not from the internals of PSSE, but you match to a modeling that you have, in the case Modelica source file, and then you make sure that you have matching results, which is similar to the approach we had.
Yeah, similar. Except that for OpenIPSL, you can get it for free for years. I don't even have it. I only have eMegaSim and eSearchSim.
Yeah, understood. Thanks.
Okay.
Bertrand?
Hello. Hi, it's my turn. Hi.
Oh, hello.
Hello.
You're going to the general meeting next week, huh?
Yes, I'm really sad that you said that
see?
actually that you are not coming.
Lucky you, you're rich guys, huh? With funding, not like me, a peasant that the DOE rejects all of the grants.
Okay, then I will have to stop and pick you up then. Like anyway, I will fly somewhere over. Try so I can pick you up maybe.
Yeah, throw me a rock.
Anyways, nice to see you. Yeah, we need to catch up also on other things, actually, what is happening, but also like, thank you for the really interesting presentation. I, of course, always like your enthusiasm about these things or these different tools and how you are handling. But yeah, the question then at the beginning, you started more about these multi-domain, multi-energy gas grids and all that, but later you were talking mostly about this transformation in PSSE and this kind of a dominance of the tool. Is there some kind of like some comments regarding these other tools, or have you looked at other tools, gas and heat grids for modeling and this kind of equivalent between these tools?
To be honest, I don't need to, because you wrote a paper with Thomas and you did all the job there. So why should I spend my time doing it? Secondly, I mean, at this point of my life, I have wasted so much of my time, and you know, the only thing that we have in life that is irreplaceable is our time. And I have wasted it with so many tools, re-implementing models 10,000 times, that I'm fed up. So for me, I'm only trying to do everything with Modelica, because we're talking about, you know, with OpenIPSL, there's models that are 10 years old and they still function well. So I don't think there's anything else I can pick up as an academic that will give me that longevity. Most people in academia use MATLAB and Simulink, and it just breaks constantly. So from that point of view, I'm trying to just do what's it called? Do everything in Modelica. There are tools to do the gas networks. They have different formulations on how they do the fluids. Some of them are basically long parameter models. For example, Syncal has that. But that doesn't let you do dynamics. So, I mean, if you have a gas turbine, you kind of care of what you're doing to it. And that involves changing a little bit. When you change of operating points, you have all these complicated enthalpy and entropy curves. So I think it's a little bit difficult with that side, because it's also the same problem that we have in power systems, that every specific program has their own specific file formats, and you will have to do things like what I'm doing here if you want to translate large models, right? Or, I mean, for academic things where you're doing things with small models, I mean, just build it by hand. That's the answer that I give to people, because, you know, why kill yourself trying to translate models if they're small? It's no point. It takes you 2 days. I mean, takes me 2-3 days to do it. And to get it a power system model you give me a small one, it'll take me 2-3 days to get it perfectly implemented in Modelica, and then I don't have to ever do it again, right? So
yeah, no, thanks.
Sorry, I don't have anything else.
Hussein?
Oh, thank you, Luigi. Great presentation. I know that we're on top of the hour. I'll ask my questions quickly. So
I have time, Hussein. No, don't worry.
Thank you. So what I've understood from your presentation is that traditionally when we do model conversion, it's like just converting parameters from one platform to another simulation platform. Now you're taking one step beyond that, and not only parameters but also the mathematical representation is also transmitted from one platform to another platform. Now,
so basically, if you look at converting parameters, if you look at this file here, I'm converting the parameters in sim of the power flow, the values of the initial voltage. They are parameters that go into the Modelica model that I am using. The Modelica model has the equations.
Yep. Yeah. So now what happens when the two simulation platforms have different solvers? Wouldn't that also impact or somehow introduce some discrepancies, even though the parameters as well as the mathematical representations are the same?
Yes, it does, and it depends what you're talking about. So if you do it within a Modelica tool, your Modelica model is fine, but if you're bringing another model into a Modelica tool via FMI, and that model is in co-simulation mode, then it's going to already have a solver, and the master simulation tool will be the Modelica tool that will take care of synchronizing the time steps. So Daimola will import an FMU, and you will run the whole grid with, I don't know, some manufacturer model of a PV. Daimola solver has to take care of doing that, synchronization and so on. Conversely, now the other tools don't use Modelica at all. All of the tools for power system, the only one that I know that does offline analysis. Oh no, well, there's two tools. It's ePhaser Sim and Dick Silent Power Factory, where you can use FMUs. And what they do is that they have the master simulation algorithm. And that master simulation algorithm takes care of giving inputs, waiting for the output, and doing the overall solution of the network plus each of the outputs of the components. Yeah. I think also EMTP also uses FMUs, by the way. I don't want to leave it out, but that's for EMT. I don't, my library doesn't do EMT.
So in simple terms, if I have a model in the Modelica language, and if I create FMUs out of it, and I export that, or I use that FMU in platform A and in platform B, are they going to generate exact same results, or are they going to be slightly different because the solvers in platform A is different from the solver in platform B?
Yeah, this gives me the opportunity to pitch in that I offer courses about Modelica and FMI. I get paid so poorly, I gotta do something else in life, right? So no, you have to check the FMU when you generate it. You have to check it in the tool that you're generating it first. And then you have to check it in the other tool. Okay, so let me show you really, since I have time. If you have time, I don't mind. Let me show you an example here. So when I teach this, I have homeworks, assignments, and where is assignment FMI solution here. So here I'm translating a model. So this is just model exchange. So FMI has three ways that you can export the model from Modelica or from C, if you wrap it around FMI or whatever. It has three modes that you can export it from. Model exchange, which means that the equations are they are casualized The equations are casualized, so there is no more acausality like in Modelica. They're casualized, and then they are put into the FMI standard, which means that how you access the functions of the equations from the other tool. And then the tool, in model exchange, the tool is running the entire simulation, including the FMU. So there you don't need to synchronize. That's model exchange. There is also co-simulation. Let me pop up my slides really quickly to be a little bit clearer and take a step back, because I am confusing things, and that's not good. So let me see here. Where's it? Yeah, so FMI. Really, the FMI was developed by the automotive and aerospace community, mostly in Europe, to solve this problem of building complex systems where you have different vendors of different parts, and you need to do a system integration. This is kind of what power system analysis is nowadays. But they created this standard so that they could have a common interface, and now is supported by more than 150 tools. And so there is these two, there's three. I don't have the third one here because I haven't updated my slides. FMI 3 just came out. This is up to FMI 2. So you have the FMI standard gives you a set of C functions and a shared library with the model's equations that I casualized, and an XML schema that has all the variable definitions, model metadata, and parameters. And you can export it in this way. So if you have model exchange, you have only the model equations here, and the master simulation tool will solve everything. In co-simulation, you will export an FMU that includes a solver, okay? That's, for example, CVOD. So if I go here into one of the examples, just very quickly, and I go to translate, I can tell it, right? Give me model exchange or give me co-simulation with CVOD. So you will have the CVOD solver included with it, okay? So those are the two, and in that case, the master simulation tool has to provide inputs, wait for the solution, and retrieve outputs. And it has to do this for each FMU and coordinate the solution with whatever else it has inside. I hope that.
No, that's very interesting. And the second question, you mentioned about multi-domain simulation.
Yeah.
How did you do it with Glenn? You mentioned something like if the gas.
Well, I have a better, we're looking into how to do it, but the problem is that all the grants get rejected, so.
Okay, so you're
but
going
let me show you one. Let me show you one. Multi-domain. Let me see here. So this is one example. This is another library that basically what we have built is a variable speed drive that connects to a motor, and the motor connects to whatever you have, whatever process you have at the rest of the load. So just as an example here, so here, for example, you can connect anything to the flange of the motor. So that's one example. Here's the one with the variable speed drive. And here, so this is a good example, you see? So here we have a fluid system where we are driving through the induction machine, through the shaft. We're driving a pump, and we have a valve that opens and closes and fills a reservoir. This is a simple example, right? So on the load side, you can do multi-domain, and on the generator side, what you will need to do is that if you have a gas turbine, instead of using our simplified models, you have to, let me find here the other paper that I have. It's a little bit older, so give me 1 second. Multi-domain, let's see. It's been a while since I opened this. Drones, no drones. Oh yeah, so here we modeled a nuclear power plant connected to the grid. And so what we had to do is to replace those simple transfer functions that we have inside of normally the power system models and interface the power system model. So here you have gen row, you see? Yeah. And we interface that to a mechanical shaft that is here. So you see here we have a boiler. After a boiler, we have the turbines. And I forgot what this is. I think it's a condenser. I don't remember. And finally, you connect to the generator. So this is a thermofluidic and mechanical model of the steam turbine. So you can do that on that side. If you wanted to do gas, so here you see the input into the steam turbine is steam, so that's the boiler. This is the turbine or the balance of plant, because the turbine has more than a turbine inside, really. And this is the generator, and this is the power grid that is inside. That is just a single machine infinite bus.
So Luigi, when you do multi-domain, the time step of the simulation is the same for all of them or different?
No, because the beautiful thing about Modelica is that you do not tools is that you can use variable step time solvers. So you can here, instead of use a fixed time step solver, you can just go and select the all powerful DASL, and now you have a variable step time solver. So it's not fixed time step, it's variable time step with tolerance error control.
Okay.
Right? So there you go.
Okay, thank you.
So, yeah, no problem.
Yeah.
By the way, there is also other examples from my friend in Norway, Dietmar Winkler, that he has done an example of using the OpenIPSL, Open Hydropower Library, where instead of having some transfer functions, he actually models the penstock, the pipes, and everything. You know, so this is something that he also uses OpenIPSL to do this. I don't have it right away, but I can send it to you if you're interested. I mean, the moral of the story is that I'm trying to bring all these power system models, even the big ones, if I can, into the Modelica ecosystem so I can do these things. It's been challenging, right? 10 years of this nonsense. We still have 15 people. Anybody wants to ask anything?
Yeah, I think we are 13 minutes, around 30 minutes past the hour. So thank you, Luigi. And before everybody goes, I mean, again, we will have in-person meeting during IEEE PES general meeting on July 23rd between 11 a.m. to 12 p.m. in room number 330. So if you are attending and if your schedule permits, please attend. And thank you very much to our speaker and everybody who participated in this seminar. Thank you.
Thanks, everyone. Bye-bye.
Thank you.
Thank you very much, Luigi.
Hey, Jan, nice to see you.
Very
Old
good.
friend.
Bye.
Bye.